So we've worked through a sample calculation. Now let's repeat everything we did for all of the data points. So different masses of the antacid, always dissolved up in 25 cubic centimeters of the HCl. Knowing the concentration of the HCl, I get the moles of the HCl. I then used it titrated with sodium hydroxide to get the moles of sodium hydroxide to see what was left. So therefore the moles of the calcium carbonate, moles of the HCl with which I started, moles of NaOH is equal to the moles of HCl that's left. So therefore the moles of HCl used up by the calcium carbonate is simply this pink column minus this blue column, but then divided by 2 because each calcium carbonate uses 2 H pluses. Go to grams, and then percent of the calcium carbonate is simply the grams of calcium carbonate over the grams of the antacid that I took. Now, whenever you do lots and lots and lots and lots and lots of data, you go through and you're going to average it. But before you average it, you go and see, are there any sort of weird ones that stand out? So we got 62, 62, 61, 59, 63, 61, 62, 63. So there's a possibility that this 59.8 is a weird one. Now, the test that I use for whether or not a particular piece of data is a weird one, is an outlier, should be rejected, is I will calculate the mean without it. I'll get the standard deviation without it. I will then compare the value, 59.8, to the mean, and if the difference between them is more than 3 times the standard deviation, then I will reject that piece of data. So ignoring the 59.8, the day of the mean is 62.4. The standard deviation used without this is 0.68. Okay, not going to go into how you calculate standard deviations. Essentially, your calculators in Excel do it for you quite nicely. But the standard deviation is simply the average difference of each data point from the mean. Okay, and so if it deviates too far from the mean, it's probably not a very good piece of data. So anyway, let's see, we got the standard deviation is 0.68. We're interested in 59.8, which is 2.6 away from this mean, and 2.6 is 3.8 times this 0.68, 3.8 times the standard deviation. Thus, I will reject that piece of data. So let's look at the Postlab questions, the first part of the Postlab questions. First of all, what's this buffer formation? What does it do? Well, when we've got carbonate and we titrate it with H+, it makes hydrogen carbonate or bicarbonate. And if we titrate that further with H+, we get to carbonic acid. Okay, the trouble arises with this bicarbonate presence in there because it is amphiphilic. Bicarbonate in water can act as a base to make the carbonic acid, picking up the H+, or hydrogen carbonate can react with water such that it acts as an acid, donating the proton to water, leaving behind the carbonate. So because you've got all of these substances created in there, and one of them is this amphiphilic nature, you've got not just one buffer, but you have a double buffer in there. Now, buffer solutions, of course, resistant to pH change, you get these weird equilibria established. It will confuse the results as you're going through the titration. Although ultimately, if you're patient, you will, with care, get the same result as we're doing with our back titration. And I should also point out that, of course, 2 of the other WJEC specs are associated with titrating carbonates up here. You have the back titration and you have the, you have the double titration and you have the standardization of an acid. So 2 other experiments show that you can get away with titrating carbonate with HCl, but it can mess things up a little bit. And in this case, we're just using the reaction to illustrate the back titration. Question 2, why did I heat it up before titration? And this was not to speed a reaction up. What it is to help dissolve the calcium carbonate. Calcium carbonate, of course, is insoluble in water. It is soluble in the acid, which is why we add the acid straight to it. But we do want it all to be dissolved up in there. So good idea to heat it to help that. And then, of course, CO2 dissolved in water, right? That is part of this whole reaction sequence right here anyway, so you want to get rid of any CO2 that you have there at the start. Otherwise, you'll confuse your results. And question 3, what we talked about on the last slide there. Calculate the percent calcium carbonate in antacid A. If we didn't use all the data to explain why, we averaged 62.4%, and we didn't use trial number 4 as it was more than 3 standard deviations away from the mean. So let's go back and think about antacid B, doing the same calculations for these. Do note, and we'll address this in the Postlab questions, that I did 4 using 25 cubic centimeters of the HCl and then 4 using 30 cubic centimeters of the HCl. This not only increased the amount of HCl I was adding, increased the amount of the NaOH that I was needing to find out how many HCl moles were left. Anyway, the percent value for calcium carbonate for each of these, doing the same calculations, comes out to be about 40%. So antacid A about 62%, antacid B about 40%. Again, before we do the average, let's peruse and see if there's anything that stands out as being weird. And we got about 39, about 39, about 39, about 39, about 39, 40, 39.5, 39.4. So if there's one that leaps out, it would be that 40.1. Okay, now the way that, again, working it out is I'll calculate the mean without using that. It's 39.1. Standard deviation without that is 0.29, so about 0.3. And the difference between the mean, 39.1, and the value is, of course, 1. And 1 divided by 0.29 is 3.45. So again, the difference between this value, my outlier, and the mean is more than 3, quite a bit more than 3 times the standard deviation. So I will not use that particular data point. Returning to the Postlab questions. Some of the measurements in B, I increased the amount of HCl I added. Why did I do that? What the advantages, if any? If you remember, I went from 25 to 30 cubic centimeters of HCl. The reason for that is we just reduced the effect of systematic errors. Now we do this in this case in both the pipette for measuring the HCl as well as the burette for measuring the sodium hydroxide. I'll just focus on the pipette, but it's the same argument. The error in using the pipette is plus or minus 0.05 cubic centimeters, and that's an error regardless of what you do with the pipette. Okay, now in 25 milliliters, that's 0.2% error. However, as we increase the volume, even just to 30 milliliters, we see that percent error goes down. Generally, the more that you can measure, a larger measurement as possible, the less significant errors in measuring become. Now, of course, there's a limit to that. You don't want to sort of start using gallons and gallons and gallons of solution, because then you have issues with glassware, you have issues with economics and so on. But where you can, try and go as big as possible to reduce the effect of these systematic errors that are just inherent in any kind of measurement. Question 5. Calculated at 39.1%, didn't use trial 3 because the value was more than 3 standard deviations. So now let's look at the actual antacid part, which is the better antacid. Well, antacid A is 62%, the calcium carbonate. Antacid B is less than 40%, so antacid A is better because it has more active ingredient per gram. And now an interesting one, antacid A costs $1.50 for a pack of 12, B costs £2 for a pack of 12, which is better in terms of cost per relief, and assume the tablets are the same mass. Well, A works out as 12.5p a tablet, and B is 8.3p a tablet. So in other words, a tablet of B is cheaper than a tablet of A, but of course A has got more antacid in than B. Well, the ratio was about 60 to 40. Okay, or about 1.5 times as much active ingredient in A as B. So if we multiply B by 1.5 to make it equal, we get about 12.5p. So in other words, the increase in the carbonate content in A is pretty much offset by the increase in cost in A. So therefore, there's no real difference between the cost per relief between antacid A and antacid B. Hope you enjoyed it. Hopefully see you in another experiment.